Section: Introduction. We're looking at how to improve the problem-solving abilities of advanced language models, like GPT-4 and PaLM-2, when it comes to mathematics. These models are already showing promise, with their chances of finding the right answer increasing when they're allowed multiple attempts. For instance, the pre-trained PaLM-2L model can achieve an accuracy of about 33.4% with a single attempt, but when it's allowed to try 64 times, it gets at least one correct answer 79.4% of the time. This suggests that these models can generate correct solutions, but they struggle to distinguish between right and wrong ones. To address this, we're exploring three methods to fine-tune these models. 1. Supervised Step-by-Step Solution Fine-Tuning, SSFT. We're looking at whether these models can benefit from a supervised fine-tuning stage, where they're trained to generate step-by-step solutions and final answers. 2. Solution Cluster Re-ranking, SCR. We're also trying to improve the model's ability to evaluate solutions by fine-tuning it to re-rank candidate solutions. We're using a new technique that combines the benefits of majority voting and re-ranking, while also reducing ranking costs. We group candidate answers into clusters based on their mathematical equivalence, then apply the solution evaluator to the solutions in the most common clusters to improve on the majority voting results. 3. Multitask Sequential Fine-Tuning. We're interested in improving the model's performance on both the solution generation and evaluation tasks. We're proposing a sequential multitask learning setting for the generation model, where the solution evaluation task is formatted as a natural language generation task. This way, its training objective can provide meaningful supervision to the solution generation model. We fine-tune the model in a sequential manner, first as a solution generator, SSFT, then as a solution evaluator, SCR, and finally as a generator, SSFT, again. We've tested these methods on the challenging math dataset with PaLM-2S and PaLM-2L, the small and large variants of PaLM-2 respectively. Our findings suggest that the quality and style of the step-by-step solutions can greatly impact the fine-tuned model, as they benefit more from detailed, well-formatted solutions. Re-ranking solutions in the most common solution clusters can yield better performance than re-ranking all the solutions, while also being more computationally efficient. Our proposed multitask sequential fine-tuning can more effectively improve the solution generation model performance compared with supervised solution fine-tuning only, showing the benefit of training the model for both solution generation and evaluation tasks. Mathematical problem solving is an important task for measuring the reasoning and numerical computation abilities of these models. We're focusing on the math dataset, which consists of problems collected from high school math competitions, along with human-written solutions containing both natural language explanations and the final ground truth solutions. This dataset is challenging for even the most advanced language models, such as GPT-4 and PaLM-2, which can only achieve 42.5% and 33.2% accuracy respectively when given one attempt. We use the model's pass at 1, pass at n, and majority voting performance for model evaluation and comparison. Pass at 1 refers to the accuracy of the model's first solution. Pass at n refers to the model's performance when it's allowed to select the correct solution from n attempts. Maj 1 at n refers to the accuracy when n sampled solutions are first grouped by their mathematical equivalence, and then one solution from the most common group is selected for calculating the accuracy. Mic at n is similar to pass at n, but it selects the correct solution from the top k majority voting clusters. While some work has used external tools like Python programs to enhance the model's abilities, we're focusing on improving the model's inherent ability to solve math problems without help from external tools. Section Summary. Solving mathematical problems is a challenging task for large language models, LLMs, like GPT-4 and PaLM-2, but they show potential for better performance when attempting the problem multiple times. To bridge the performance gap, we explore three fine-tuning methods: supervised step-by-step solution fine-tuning, solution cluster re-ranking, and multitask sequential fine-tuning. These methods aim to improve the LLM's solution generation and evaluation abilities, leading to better performance on the math problem-solving task. Section: Methods. In this section, we'll discuss our methods for fine-tuning models to solve math problems. We aim to train models that can not only provide the final answer but also explain the step-by-step process used to arrive at that answer. To do this, we take a math problem, denoted as P, and a step-by-step solution, denoted as S, along with the final answer, denoted as A. We then use a language learning model, or LLM, to train on these inputs. During training, we combine the solution S and the final answer A into a single text sequence, which we'll call X. We then fine-tune the model using a method called maximum likelihood estimation, which involves calculating the probability distribution given by the language model. We gather our step-by-step solutions from two sources: the original human-written solutions in the math dataset, and solutions generated by a model called GPT-4. We found that the original solutions in the math dataset are more abstract, while the solutions generated by GPT-4 are more detailed. We also noticed two significant gaps in the math problem-solving performance of LLMs. The first gap is between the model's initial solution and the solution arrived at by majority voting. The second gap is between the model's best solution at one attempt and its best solution after multiple attempts. To address these gaps, we fine-tune the LLM to act as a solution verifier or evaluator. We then use this evaluator to score each potential solution. We do this by turning the scoring task into a classification problem. We create a prompt that includes the math problem and a potential solution, and then predict whether the solution is correct or incorrect. We then use this prediction to calculate a score for the potential solution. We explore two training objectives: margin loss for pairwise comparison, which compares a correct and an incorrect solution, and cross-entropy loss for classification, which treats the scoring format as a multi-class classification problem where the only valid options are correct and incorrect. We also use a method called multitask sequential fine-tuning. This involves fine-tuning the model with both the maximum likelihood estimation and contrastive training objectives. However, we found that this method may not be suitable for the math problem-solving task due to its binary nature. Therefore, we introduce a new learning setting that treats both the math problem solution generation and evaluation tasks as natural language generation tasks. We believe this approach better utilizes the capacity of LLMs, as it is closer to the pre-training task of next token prediction. In our preliminary experiments, we found it challenging to balance the two loss terms in the multitask objective. As a result, we decided to optimize the multitask objective in a sequential manner. We first fine-tuned the model as a generator, then as an evaluator, and finally as a generator again. Section summary. In the supervised solution fine-tuning method, the model is trained to generate step-by-step solutions for math problems by concatenating the ground truth solution and final answer into a single text sequence. To improve the performance of language models in math problem solving, a solution cluster re-ranking strategy is employed, where the top K solution clusters are re-ranked using a fine-tuned evaluator model. Additionally, a multitask sequential fine-tuning approach is used, combining the generation and evaluation tasks to better leverage the capacity of language models. Section: Datasets. We carried out our experiments using the math dataset. To avoid overfitting, we used the data splits provided, with 4,500 original test examples for training and validation, and the remaining 500 test examples for model evaluation. We used two sources of correct step-by-step solutions for training the model: 1. The original human-written explanations from the math dataset, and 2. The model-generated correct solutions from PRM800K, which only covers a subset of problems in the original math dataset. We measured the average solution accuracy for all the experiments. The accuracy of the generated solution was compared with the actual solution using an automatic grading script. This script checks for mathematical equivalence rather than simple textual equivalence. We used two main methods to evaluate the model performance: 1. Greedy decoding for the pass-at-1 performance, and 2. Nucleus sampling for the majority voting performance, Maj1 at n, where we used the same sampling parameters as in the original study. Specifically, the sampling temperature was set to 0.6, and the top p-value was set to 0.95. In our first experiment, we fine-tuned POM2S and POM2L on the step-by-step solutions with the MLE training objective. We explored three specific fine-tuning strategies. 1. Fine-tuning using only the original math solutions. 2. Fine-tuning using only the PRM800K GPT-4 solutions. 3. Fine-tuning on both math and PRM800K solutions. We used the model performance on the validation set for checkpoint selection, and all the fine-tuned models achieved the best performance within 2 epochs. We found that fine-tuning generally improved the model's performance compared to the pre-trained checkpoints. Moreover, the quality and style of the solutions significantly impacted the model performance, with models fine-tuned on PRM800K solutions performing significantly better than those fine-tuned on the original math solutions. In our second experiment, we noticed a large performance gap between the model's pass-at 1 and pass-at 6.4 performance, indicating that the model could search for correct solutions but struggled to differentiate its different search results. Therefore, we continued fine-tuning the models as solution evaluators for the solution re-ranking task. We used 2 loss functions, the margin loss and the cross-entropy loss, for the model training. In our third experiment, we investigated whether the training objective for solution evaluation could also help the models become better solution generators. We used the multitask sequential training objectives we proposed for the model fine-tuning. The first step was to fine-tune the model as a solution generator, then as a solution evaluator, and finally, the evaluator was fine-tuned again with the MLE training objective to regain its ability as a solution generator. The results showed that the models fine-tuned with the multitask learning objective performed better than models fine-tuned on the MLE training objective only. This suggests that the training objective of the solution evaluation task can provide useful supervision signals to the solution generation model. We believe this is because formulating the solution evaluation task as next word prediction can better leverage the LLM's ability gained during pre-training. Section Summary. The experiments in this section are conducted on the math dataset, using data splits provided by the dataset. 2 sources of correct step-by-step solutions are used for model training: the original human-written explanations in the math dataset and the model-generated correct solutions in PRM800K. The models are evaluated based on solution accuracy using 2 different solution generation methods: greedy decoding and nucleus sampling. Fine-tuning the models using the PRM800K solutions leads to significantly better performance compared to fine-tuning with the original math solutions. Additionally, re-ranking the solutions in the top solution clusters improves the model's performance. Multitask sequential fine-tuning, where the models are trained as both solution generators and evaluators, further enhances their performance compared to models trained only with the maximum likelihood estimation objective. Section: Understanding the effect of step-by-step solution style. In our research, we discovered that models fine-tuned on the PRM800K solutions performed significantly better than those fine-tuned on the original math solutions. We believe this is due to the PRM800K solutions being more detailed and closely following a step-by-step solution format. To test if this difference also impacts the performance of pre-trained models, we modified a custom 4-shot prompt by replacing the original math solution with the PRM800K solution. Our findings suggest that the performance is relatively unaffected by the difference in reference solutions, indicating that fine-tuning is necessary for the model to benefit from potentially higher quality solutions. We plan to further investigate whether fine-tuning on the model's own generated solutions with the same style can achieve a similar effect. We also evaluated the generalization ability of the POM2L solution evaluator. This evaluator showed strong performance at re-ranking the candidate solutions generated by the related POM2L fine-tuned solution generator. We wanted to see if this evaluator could also be used to re-rank solutions generated by other models. Our results confirmed the generalization ability of the fine-tuned POM2L evaluator. However, the POM2S was ineffective at re-ranking both the POM2L and POM2S solutions, suggesting that solution evaluation is a complex task that requires sufficiently large models. We compared different re-ranking strategies for math problem candidate solutions. These strategies included vanilla re-ranking, Mike re-ranking, weighted re-ranking, weighted Mike re-ranking, majority voting, and majority voting of top-end solutions. We found that the weighted re-ranking strategy performed well, and our modified version, weighted Mike re-ranking, achieved comparable performance while reducing the computational cost of the solution evaluator. Previous research introduced the math dataset and fine-tuned GPT-2 and smaller GPT-3 language models using solution and answer only as targets. However, these models achieved less than 7% test accuracy, highlighting the difficulty of the task. Later research introduced GSM-8K, a similar but easier dataset of elementary school math problems. This research showed that sampling followed by re-ranking using a trained verifier could significantly improve performance. Recent work has explored different methods for improving the math-solving ability of large language models, LLMs. Some researchers propose to continue pre-training the LLMs on math-specific corpora, which has resulted in significant improvement from the original pre-trained models. Others have extended outcome verifiers, reward models to process reward models to judge solutions at the step level by collecting human annotated labels. Some researchers have scaled human annotation of process-level labels dramatically and achieved improved performance from re-ranking using process reward models on math with GPT-4 as the base model, achieving state-of-the-art performance. In addition to training methods that directly improve the base model performance, inference time, prompt engineering techniques, such as chain of thought, and self-consistency, majority voting, have also demonstrated their effectiveness with large language models. Some recent work focuses on leveraging external tools, such as Python programs, to complement the LLM's ability, which shows further improvement over pure LLM-based methods. However, we focus on the setting with no tools. Finally, it has been shown that iteratively sampling and fine-tuning to the correct model solutions can improve mathematical performance. Although we do not employ this technique, it is orthogonal and may further improve performance.